All right, so we're going to continue working through this last section today. Just a reminder, partner quiz on Thursday, so I'll let you know tomorrow who you're working with. This last section really isn't anything new to us per se. It's just the concept of solidifying or letting it sink into our heads what a derivative is, what it represents, how can we use it, things like that. So I believe we are on page 128 and we're on number 8. Is that right? Slope of tangent line equal to 2. When you check, does that sound about right? Okay. And I believe we labeled yesterday when the wording says slope of tangent line equal to 2, slope of tangent means derivative, and we want that equal to 2. All right, did we already find the derivative of this g equation on page 128?
No.
Did we do that at the top?
Yeah.
I think it was number 5. Okay, so we said g prime, the derivative, was 1 over the square root of x minus 1. Is that what we have? Okay, and we want the derivative to equal 2, so we're going to set that derivative equal to 2, and it's up to us to go ahead and solve for x. So algebra skills, what do you want to do? How can we get x all by itself? Go, Joseph.
Add 1.
Add 1. You want to keep going?
Multiplying with the square root of x.
All right, get rid of the fraction by multiplying over the denominator.
Divide by 3.
Divide by 3.
Square both sides.
Square both sides. All right, so at the x location of 1/9, your tangent line would have a slope of 2. Okay, visually, I'll go up to the top where our graph is. This is going to be really hard to see, but we'll try it anyway. So x location of 1/9 on the graph is maybe somewhere right there. And if you were to draw a tangent line at that spot, that would have a slope of 2. Okay, really hard to see because it's such a small location, or not small location, but really close to the y-axis in a really tight region, so it might be hard to draw. But that's basically what the information is that we represented, or that we found. So at that location, we have that slope of 2. All right, let's check out 9. Find an equation of a tangent line, specifically at the x location of 4. And when we're done with that, we're going to draw it on the graph at the top. All right, how do you guys want to tackle that one? Equation of tangent line. What do we need to identify? Go ahead, Braden.
Find the point of the slope.
Point and slope. Where does the point come from?
The original.
The original. So we're going to plug 4 into the original equation or graph, whatever is given to us. We actually have both, right? At the top of the page, they gave us the g equation as well as the g graph, so you have options. Where does the slope come from? Yeah, derivative. So we're going to plug in 4 into our derivative. Okay, so point value first. If you plug in 4 into the g equation at the top, or maybe you plug in 4 into the graph of g at the top, what point value do you get out? 2. Okay, and if you were to plug in 4 into the derivative, okay, we have that written at number 8 for you to reference if you have to. We'd have 1 over the square root of 4, which is 2. So 1/2 minus 1 looks like negative 1/2. So with the point and the slope, we can write the equation. Y minus y1 equals our slope times x minus x1. Nothing new, right? All right, we still have to draw it on the graph above. So the x location is 4. Let's go to that point on the graph. Ryan said it had a y value of 2. And if we were to draw this tangent line, I mean, we are going to. So when we draw this tangent line, we need a slope of -1/2. So from that tangent point, we should be able to go down 1, right 2, up 1, left 2, and connecting those dots, we would have our tangent line. Is it starting to sink in for us the more we do of these? Derivative means slope. Tangent line equation, you need a point and a slope. Okay, we're going to keep doing a bunch of these. Now it all depends on the information we're given. Sometimes we're given an equation, sometimes we're given a graph. If you take a look at page 128, we actually have neither. We have a table. Okay, but we can still answer some questions about derivatives and original functions based off of a table. So let's make sure we read what this table represents. The table values below represent the graph of a derivative. Okay, so this is a table of values of slope. Okay, so these are slope values, not point values. They also tell us that this derivative table or graph represents a polynomial function, like x squared, x to the third, x to the fourth. So if we think about polynomial functions, those are like roller coaster shaped graphs. They're very smooth and continuous. So maybe we'll make note of that. Okay, no holes, no jumps, no asymptotes, no like sharp points like an absolute value V graph has. Okay, they're nice, smooth, continuous roller coaster shapes. It then goes on to say the zeros indicated in the table are the only zeros of the derivative. Do we know what that word zero means? What's a synonym for that? Graphically speaking, yeah. An x-intercept. Good. Okay, so the x-intercepts have y values of 0. Thank you. Okay, so this would be an x-intercept, and this would be an x-intercept, because that's where the y value is 0. Okay, so the table represents the derivative. The original function is a polynomial, smooth and continuous roller coaster type graph. And these are the only x-intercepts we have on the graph of the derivative. Okay, so somehow that information may or may not be important, but at least they let us know that. Let's check out 10. On which intervals is the original function, h of x, increasing and decreasing? So we'll check out maybe increasing first. Can we identify, based off of this derivative or slope table, where the original function is increasing? And then we're going to provide a justification why. So when we think about the connections between original function and derivative, if we want the original to be increasing, what should we be analyzing or looking for in terms of the derivative, aka slope? Yeah. It's positive, okay. So based off of this table of slope, this table of derivative, where do we have some positive derivative values? What do you think, Braden?
Negative infinity and -2.
Okay, so since this is a polynomial, we can assume that it continues forever to the left and forever to the right. It's not like we're abruptly stopping somewhere. So if this is as far as the information goes, we're going to go ahead and assume that these values forever to the left are positive and these values forever to the right are negative. Okay, polynomials continue in every direction. So Braden said we're increasing from negative infinity to where?
-2.
-2. Anywhere else? No, because the rest of the y values or slopes are negative. And you said we're increasing there because the derivative is positive. All right, let's go ahead and check out where the original function is decreasing. Based off that table, can we perhaps find an interval, maybe 2? Maybe we can tackle the justification first. If we're looking for decreasing, we want the slope to be negative. So can we pinpoint those intervals? Good, Braden?
-2 to 7, 7 to infinity.
-2 to 7, and 7 to infinity. Notice how I'm using parentheses on -2 and 7. We cannot include those values because those values are 0. Clearly 0 is not negative. So you have to use a parenthesis instead of a bracket. Does that make sense? Nothing new, right? Okay, just a different representation. We have a table now instead of a graph or an equation to go off of. What about 11? At what x values does the original function have a max? We're looking for some type of high point. But this is the graph of the, or information of the derivative, so we need to take a look at some different type of analysis. What's the derivative doing, Justin? Go ahead.
At -2 because each prime is actually from positive to negative.
All right, so notice how at -2, your slope is 0. Okay, that's a critical point. That's a possible max or min. You have that horizontal tangent. Before -2, your derivative is positive. After -2, it's negative. You have that change in direction. So we'll say because the derivative or slope changes positive to negative, aka the original function is changing from increasing to decreasing, okay, creating that high point or maximum at the top. Okay, very similarly, can we identify perhaps where a minimum is located? Yeah. There isn't any. Why?
Because the h prime of x always stays negative, so it's level.
All right, so at this location, this is another critical point. Your slope is 0, so that's a possible max or min. But Anastasia says before this point you're negative, after that point you're negative, so you're not changing a direction, you're leveling off. That's not necessarily a minimum. So none, because the derivative never changes negative to positive. Okay, it actually stays negative before and after at that location of 7. Awesome, awesome. All right, let's check out 13. If h of 3 is 2, okay, so this is an original function information. See how it just says h, not h prime. So if h of 3 is 2, what is the equation of the tangent line at x equals 3? What is the equation of the normal line at x equals 3? So we've got to write 2 equations. One's tangent, one's normal. What information do we need to know to write the equation of any line, regardless if it's tangent or normal? Yeah. Point and a slope. Okay, so do we know the point value at this x location of 3? If you were to plug in 3 into the original function, what would you get out? Yeah.
2.
2. Okay, if you were to plug 3 into the derivative, what would you get? Yeah.
-3.
How'd you get that?
From the table.
That's from the table, right? The derivative's at the top. It's representing the table. So tangent equation, y minus 2 equals your slope times x minus that x location of 3 that we were using. What about our normal equation? Can we identify the point and the slope for that equation? What do you think, Stevie?
The slope's opposite reciprocal, right?
Yep. So that would be
1/3.
1/3. Good. And the point value? Yeah.
Same?
It stays the same. Yep. So the normal line and tangent line are perpendicular to each other at that point of tangency. So the point's not changing. Just the slope is opposite reciprocal. So y minus 2 equals 1/3 times x minus 3. Are we starting to get more confident? Okay, we're solidifying the understanding. Okay, letting it sink in. All right, find the tangent line approximation of h of 3.1. We saw something like this yesterday. This was a little bit new to us. Okay, so tangent line approximation. We already know what the tangent line is, right? We have that equation. So we're literally, don't overthink this, okay, tangent line approximation, we're going to use the tangent line to approximate, roughly figure out, if we were to plug in 3.1 into the original function, what would we get out? Okay, we don't have the original function to actually test it, but the tangent line gives us a way to approximate it. Do we remember that concept from yesterday? We drew a little picture and saw that the tangent line was really close to the original function. Okay, so we're going to take that 3.1 as an x value because 3.1 is really close to that x location of 3 that we did in the last question. So let's go ahead and plug in 3.1 into the tangent line equation. No calculator. We should be able to do this without one. 3.1 minus 3, 0.1, 0.1 times negative 3. We got negative 0.3. Add the 2 over. We got 1.7. Okay, so clearly the tangent line is close to the actual graph of the original equation, okay, at this 3.1, but it's not exactly. So this 1.7 is approximation. If you were to plug in 3.1 into the original equation, it would be about 1.7. Okay, a little off, maybe a little bit more, maybe a little bit less. We don't really know the curvature of the graph to help us figure that out. Did we discuss concave up versus concave down yesterday? Okay, we don't know anything about the curvature to help us figure that out just yet. Okay, but at least we have this approximation, roughly. Do you remember that from yesterday? Kind of? All right, let's think about this. Find the value of each of the following limits. If you were on the graph of h of x, notice the notation. Okay, on the graph of h of x, if you were to go forever to the left, what would your graph be doing? And if you were to go forever to the right, what would your graph be doing? So if we got to think about the behavior of the original function, let's go ahead and analyze the derivative at the top. So if you were to go forever to the left on the derivative function, notice how the values are positive. So in which direction can we say the original function is traveling to the left? If the derivative is positive, the original graph is what? Yeah, increasing. So we're going up, right, towards positive infinity. Let's check out the right-hand side. Okay, if you were to travel to the right on the derivative table, notice how the slope values continue to be negative. So if your slope is negative to the right, what is your function doing to the right? Are we thinking decreasing? Going down? Okay, so if our function's going down forever, that would be towards negative infinity. We doing okay? Different pieces of information, graphs versus tables versus equations. We can still analyze increasing, decreasing, maxes and mins, all that fun stuff regardless on what we're given. All right. So in this example, we were given the table of the derivative, okay, just specific values. Let's go ahead and check out the one on the back. Let's see what we're given here. The derivative of a polynomial, okay, a smooth continuous function, is given by this equation. Okay, so we have the equation of a derivative this time, not a table or a graph. Use this equation to answer questions 16 through 20. All right. On what intervals is the original function increasing, decreasing? Justify your answers. All right, so let's see what we can do if we have an equation. What might be useful to find based off of that derivative equation? Let's see, if we're concerned with increasing and decreasing, we want the derivative to be positive. We need to figure out where the derivative is negative. What might be useful for us to figure out from that derivative to kind of section off these positive and negative locations or intervals? Remember our vocab word? Yeah, critical points. Okay, so that's when the derivative is 0. Okay, we'll find those critical points. All right, so they give us the equation of the derivative at the top. If you were to set that derivative equal to 0, let's see if we can figure out those critical points. Okay, imagine putting a 0 right there. That's the equation of the derivative. What would make the first factor equal 0? What would make the second factor equal 0 and the third? Can we pick them out? 0, 2, -3. Those are the critical points. All right, so they're telling us that the original function is a polynomial. Okay, nice, smooth, continuous kind of roller coaster graph. So in terms of the domain of a polynomial, those go forever to the left and forever to the right. Those would be all real numbers. So we're going to go from -infinity to +infinity, but use the critical points to break up that interval in order. So -infinity, -3, -3 to 0, 0 to 2, 2 to infinity. So we're going to analyze what is the derivative doing on those intervals, and based off of that information we should be able to conclude what the original function is doing on those intervals. What's a number between -infinity and -3 that you want to pick? -4. Okay, so we're going to plug -4 into the derivative equation. They gave that to us at the top. Okay. If you plug in, remember, we're not concerned about the number, we're concerned about the sign. We're looking for is the derivative positive or negative. So if you plug in -4, this factor would be -4, this factor would be +6, and this factor would be -1. So negative times positive times negative. What's our derivative going to be? Negative times positive times negative. Positive. I don't care about the number, I care about the sign. So what's our original function doing? How's it behaving? Increasing. Good. All right, pick any number you want between -3 and 0. -2. All right, first factor, negative. Second factor, if you plug in -2, positive. Third factor, if you plug in -2, positive. Negative times positive times positive. We got negative. So original function is decreasing. Something between 0 and 2, most likely 1. Positive times positive times positive. We got positive. And anything bigger than 2? We got positive, positive, positive. Oh wait, no, that would be negative, right? That would be negative. Positive, negative, positive. Alright, so based off of this informational chart, we should be able to answer these questions. Where are we increasing, where are we decreasing? Maybe we'll start with increasing first. F of x is increasing on the intervals, let's see, negative 3 to negative infinity to negative 3 and 0 to 2 because we found the derivative was positive. We can write a similar statement for decreasing. F of x is decreasing on the intervals of negative 3 to 0 and 2 to infinity because the derivative is negative. Nothing new, right? Solidifying, letting it sink in. All right. At what x values does the graph reach a minimum? Maybe you have to reference the chart to help you with that. Okay, can we identify perhaps where we have a low point? They just want the x value, graphically the location of it. What do you think, Stevie?
0.
Why?
Because it goes from decreasing to increasing.
When you say it, what do you mean?
The derivative, or negative to positive.
All right, so the derivative goes from negative to positive. You could say also the original function changes decreasing to increasing, either one, okay? I want you guys, I know explaining things is not the norm in math classes, but if you can be as specific as possible, that would be better. So no using it or the graph, okay? You need to say the derivative, the original function, the graph of the derivative, the graph of the original, something like that. Okay, try to be as specific as possible. So x equals 0 because perhaps the derivative changes negative to positive. Okay, very similar question for 18. At what x values do we have a maximum? We don't necessarily have to find the height of these points. We just want to know the x location. Can we figure it out based off the table? Go ahead, Stevie.
X equals negative 3 and 2 because the derivative changes from positive to negative.
Derivative changes positive to negative. Yep. You can say original function changes increasing to decreasing. Same idea. Alrighty. Let's check out 19. If f of 4 is negative 1, what is the equation of a tangent line? Let's see, point, slope, let's check it out. We're specifically looking for x location of 4. So if you plug in 4 into the original for the point, looks like they told us that would be negative 1. And if we plug in 4 into the derivative, we got to figure out our slope. Remember the derivatives at the top, that equation they gave us? So if you were to plug in 4 up there, what would you get? 4 times negative 2 times 7. Good, Braden?
Negative 56.
Negative 56. All right, so equation time, y minus, or plus 1, equals our slope times x minus that x tangent location. We had 4. Hanging in there? I hope we're starting to feel confident. All right, last one for this set. Approximate the value of f of 4.1. If we were to plug in 4.1 into the original equation, if we had it, what would we roughly get out? Okay, so we don't have the original to actually check this, but what might you want to do? How can we approximate a function value? Do we have some piece of information that's kind of close to the original function at this 4.1 location? What do you think? Alexis, can I pick on you for a second? Saw you shaking your head.
You can just plug in 4.1 into the x value for the tangent.
The tangent line. Okay, so at this x location of 4, that's where we drew our tangent line. Okay, if you visualize it, I have no idea what the original graph looks like. This is just going to be a rough sketch. So I'm going to say this is the original graph. Here's my x location of 4. And if I were to draw a tangent line, okay, somewhere only touching once, notice how the tangent line is really close to the actual graph, a little bit off of that 4 location. Okay, just slightly off. So even though we don't know the equation of the blue line, okay, the original function, we do know the equation of the tangent line, okay, that red one. So let's go ahead and plug in 4.1 into the tangent line. Okay, this is going to give us an approximation, something close. Clearly those two black dots are not exactly the same, but they are very close to each other. Okay, without a calculator, 4.1 minus 4, we got 0.1 times negative 56. Negative 5.6, you're just moving a decimal. Add over the 1. We got negative 4.6. Or sorry, subtract over the 1. My bad. Negative 6.6. So if you were to plug in 4.1 into the original function, it would be about negative 6.6. We're slightly off. We don't really know the curvature of the original function to determine if it's above or below. Okay, this was just a rough example. Okay, that's just how I drew it. I don't know if that's actually what's happening. Okay, but at least we know that's roughly about what it is. Explain why this is a good approximation. How do we know for sure that this is fairly close to what the actual value is? What do you think, Vinny?
Well, since it's only 0.1 of 1 away from it,
Uh-huh.
really close to the actual value, really close to the actual value, the closer the line is to the
The more accurate you are. Okay, so this 4.1 that we're testing is really close to that tangent point that gave us that tangent line equation. Okay, so we'll say the x value being evaluated is very close to the tangent point. And because the closer you are, the more accurate you are, the closer your approximation is going to be. Make sense? Okay, because based off this example, if I were to pick something like 5, remember this is location of 4, 5 is further away, and notice how the tangent line, the difference between the two is getting larger. So your approximation is getting less accurate. We need something very close to that tangent point. Solidifying? Sinking in? Okay, we're going to save the last example for tomorrow. Okay, I know we still have a little bit of time left. Maybe you want to start some of the homework for this section. This last example is not going to take us all day tomorrow. So that means the rest of the time tomorrow you can use to help prepare for the partner quiz. Maybe, I am going to let you know who you're working with. Maybe you guys want to pair up and get a game plan ready. Okay, if you want to do that. but the rest of the day tomorrow is going to be yours to help you prepare. Okay?